Jock here for second part. I linked a simulation down below. It only works with computers, not phones. Sorry about that. But we're going to go over some of the basic ideas of what affects motion in a non-math setting. Because as you know from this class, you have to do a lot of predictions based on certain situations. So up here we have adjustable angle degrees, initial speed, mass diameter, and a check for air resistance. These two things right down here only affect the air resistance, so we'll leave them alone. We're going to come up with a couple quick solutions on what can happen under different conditions. So here's 60 degrees. I'm about to fire it off. It's going to go pretty high, but it will not go as far as it normally could because it doesn't have enough forward motion to make use of the extra flight time it has from its y velocity. So this is its delta x. This is its delta y. That's its time in the air. This little black cross represents where it's at after 1 second. Now, it ends up below where it starts because the ball starts here, which is above the ground. What angle should I point this cannon at to theoretically have it hit at the exact same place on the ground? Hopefully you set a complementary angle, 30. Let's try it out. Kinda. Notice how the 30 went further. That's because it's not exactly at level height. If it's the ball started here, the cannonball I should say, if you look at this baseline here, both the 30 and 60 ended or hit at the exact same distance away on that zero line, but they hit at much different times. So the top one at 1 second was a little bit over halfway there. The 30 at 1 second was pretty much hitting. But now since there's extra distance to fall, the 30's forward velocity allowed it to go a little bit further in that extra time than the 60-degree one. So what angle should make it go the furthest if it starts here and we're looking at this as your endpoint? And hopefully you said 45 degrees. At delta y is 0, the 45 degrees is the most efficient use of its time and its forward motion. It had a little bit less forward motion than the 30, but the extra time allotted by its upward motion allowed it to go further than the other one. So there's a relationship between kind of hang time and forward motion to see how far they go. When you go to extreme cases, like you start off very high and you end up down below, it's different. Well, it's the same idea, it's just that you have to apply it differently. Let's look at 60 degrees. Did the extra hang time in the air allow it to go further than it normally should? We'll take a look at 30. No way. Because the hang time of the 60 is so little compared to the time it's in the air afterward, the 30's extra forward motion allows it to go even further than the 60. Let's look at 45. The 45 doesn't go as far because its extra hang time it has above this white line does not compensate for the 30's extra forward motion and the time it has afterward. So in other words, a little bit of extra hang time it has from its upward part is overwhelmed by the forward motion that the 30 has to use in this section down here. So I bet I can maybe 30. Let's try 25 degrees. Ooh, pretty close, but it's barely a little bit further, you may have noticed. In this case, the 5 degrees less means it has a little bit more forward motion, and a little bit less hang time it has allows it to go even further. But if you go look at, let's say, 15 degrees, 15 degrees means that the less hang time it has is not overwhelmed. Or in other words, the 15 degrees, its forward motion it has, is not enough to compensate for the lack of hang time in the above time section. And finally, let's bring this down. If you're trying to hit something in the air, so if you're looking at a point where above where it's at, obviously the y part plays a bigger role here. So again, some of the rules that we just talked about are true. So in conclusion, when we're looking at how things affect each other, it's a balance between hang time and forward motion in what you're trying to do. We're going to look at some examples in class. We're going to play around, do a lab about it, and eventually you'll be very competent at these ideas. Play around, see what happens. Try to place this in different places and try to get hits. And I wish you well in the quiz next time. Good luck and have yourself a great day.